Good afternoon. My name is Francesco Musiale. I came from the Industrial Engineering Department of the University of Parma. And I would like to introduce to you the work that the team in which I am inserted, guided by Professor Alessandro Pierondi, has carried out in collaboration with the team of Professor Zucchelli from the University of Bologna. It is related to the possibility to extend to adhesive bonding joints some advantages previously gained in some composite laminates by using a technology based on the interleaving of nylon nanofiber mats at the interfaces between adjacent layers. In fact, in the past, many authors, including some of the current work, had already developed studies dealing with the possibility to substantially increase the energy dissipated by the laminations by using nanomats at the interfaces between the laminate layers. As you can see in the top right of the screen, there is a comparison between the low displacement curve obtained during a low velocity impact event in a virgin laminate and a nanomodified laminate, in which some nanomats were placed at the interfaces. Although the critical value of the energy dissipated in the nanomodified laminate is lower than the virgin one, the amount of damage dissipated energy increases as the impact event proceeded. You can also see a contour plot extracted from a finite element model showing some differences in the laminated area extension between a nanomodified interface and a virgin one. In the past, a few authors, like Ho and Kim, in a 2014 work, evaluated the adhesive strength of metal-to-metal adhesive joints by using a meta-aramid nanofiber reinforced resin to, as I said, reinforce the adhesive strength of the joint. Our idea was to try to use the same polymeric mat successfully used for composite laminate in order to reinforce even the interface and the bond line of the adhesive bonding joint, making the nanomat act as a sort of bridge effect between the adjacent layers and using it as a carrier for the adhesive. To assess the effectiveness of the procedure, the values of the mode 1 fracture toughness with and without the reinforcement were evaluated through an experimental campaign of DCB tests and were compared. Firstly, let me spend a few words to describe the electrospinning technique used to produce the nanofiber mats. The polymeric solution with some solvent was injected into a capillary tube and then in a needle, kept in tension by a highly voltage power supply. When the electric field reached a threshold, the repulsive electric forces became stronger, became higher than the surface tensions, and therefore the polymeric solution was ejected from the needle and was whipped in the path between the needle and a ground collecting plate, in which the electric charged jet was divided by the electric field into a multitude of nanometric fibers stacking on each other to form a mat whose thickness could vary from some micrometers to some nanometers. In the current case, our mat has a thickness included in the range between 70 and 90 micrometers, while the nanofibers have a diameter of 150 50 nanometers. A first experimental campaign is now discussed. 2024 G3 aluminum panel was manufactured in order to obtain some 300 times 25 times 15 millimeters adherents. The side of the adherent which was aimed to be bonded was sanded. And two configurations of specimens were considered, the so-called virgin configuration without the reinforcement, and a nanomodified configuration in which a nylon 6.6 nanofiber mat was placed at the interface. In the virgin specimen, MTA 240 Cytec epoxy film was laid down on the first adherent. Then a polyester sheet was used to produce the initial 40 mm long crack. The adherent was placed into a bonding template and the second adherent was put on it. In the nanomodified specimens, instead, after that the epoxy film was laid down, a nylon nanomat was stretched out on the epoxy film in order to make it impregnate as much as possible. This is the stacking configuration of the nanomodified specimen. The bonding template went into a vacuum bag, which underwent a 1 hour curing cycle in autoclave at a temperature of 120 Celsius degrees and a pressure of 2.1 bar. DCB tests were performed according to the international standard ASTM D3433 in displacement control at a constant crosshead ratio, and the values of the crack opening displacement were measured by using an omega clip gauge. In order to obtain a crack with a sharp tip not artificially created, a fatigue pre-cracking phase was performed until the crack propagated for 5 millimeters. Since the pre-cracking phase, we noticed that there was a decrease of the energy necessary to make the crack propagate in the nanomodified specimens with respect to the virgin one. DCB tests were performed applying a load-unload law in order to obtain in the declining part of the force displacement curve some reload sections with a constant slope, which allows to evaluate the specimen compliance and therefore the actual crack length. The values of the strain energy release rate were evaluated using the crank model, including the parameter lambda used for the correction that the crank required. These are the results. Unfortunately, there was a dramatic drop of the G values in the nanomodified specimens with respect to the virgin one. Analyzing the fracture surface, it is possible to notice how part of the epoxy resin managed to pass through the nanomat and depositing itself on the adherent, initially in contact only with the nanomat. But a separation between the nanomat and the resin occurred. In fact, as you can see on the top adherent, the nanomat is discernible, while on the bottom adherent, the blue epoxy film occupied the whole surface almost without a visible trace of nanofibers. This one is the stacking configuration of the nanomodified specimen after that the breakage occurred. SEM analysis revealed that both the virgin and the nanomodified specimens present a relevant level of porosity, probably due to a high viscosity of the resin, which prevents the complete ejection of the air. In the nanomodified specimen in particular, the level of porosity was very high because the nanomat does not succeed to evacuate completely the air trapped within, which results in a decrease of the mechanical bonding properties. Furthermore, the the resin does not manage to fully impregnate the nanomat, which contributes to make the bonding process fail. A second experimental campaign was performed in order to limit the level of porosity. The curing cycle occurred under vacuum, and an epoxy thermosetting impregnation resin used for manufacturing of woven prepregs with carbon fiber was used instead of the more viscous epoxy film in order to make the resin flow into the whole thickness and to make it impregnate, to fully impregnate the nanomat. Some 60 micrometers thick metal sheets were placed at both the extremities of the specimen in order to make the thickness of the virgin specimen as uniform as possible with respect to the nanomodified specimen, in which, however, the metal sheets were placed to assure that the nanomat occupied the whole thickness of the interface, even if it had been squeezed during the curing process. And the vacuum bag went into a 3-hour autoclave curing cycle at a temperature of 100 Celsius degrees and a pressure of 6 bar. These are the results. The force is plotted in function of the crack opening displacement. These are the cures relative to the virgin specimens, and these are the ones relative to the nanomodified specimens. We can already see how the N01 specimen dissipates an amount of energy lower than the virgin one. The N04 specimen dissipated an amount of energy higher than the virgin ones, while the N02 and N03 specimen present a first peak, a first critical value of G, lower than the virgin one, but then it increases as the test proceeded. Here we have the strain energy release rate values plotted in function of the crack length. We can see how the N01 specimen, the N01 specimen curve remains always lower than the virgin ones, while the other three nanomodified specimens, in the other three nanomodified specimen, the wild increase of the G values with respect to the virgin one occurred, even with different degrees of success. In fact, the N02 specimen increases the value of G linearly, starting from a value that is lower than the virgin one, and ending when the crack length is approximately 160 millimeters with a value that is higher. The N03 specimen shows a similar trend, and the N03 specimen is the one which exhibited the best behavior because it's the one in which even the G value associated to the first peak is higher than the virgin one. Optical microscopic analysis revealed that the nanomat does manage to occupy the whole thickness of the interface, managing to structuring the bonding. And a cohesive breakage of the nanomat actually occurs because it left an extremely thin alloy of nanofibers on one adherent and a more thick portion of it on the other. SEM analysis confirmed this hypothesis because even when the surface seems smooth, actually there is an alloy of nanofibers covering the metal to indicate that the crack propagates very near to the interface, to the bond line, but does not manage actually to reach. To conclude, the use of an iron nanofiber mat to improve the resistance to the bonding is possible. Even though the experimental campaign is still limited, at the moment results indicate an increase of the value of G with respect to the virgin specimens, and a more detailed study has to be performed over the critical value of G at the initiation of crack growth that at the moment occurs only in one case. Thank you very much.